here is my reassessment for chapter 22.2, which deals with Ampere's law. Ampere's law is very similar to Gauss's law, but instead of relating electric field to charges, Ampere's law relates the patterns of magnetic field around a closed path to the amount of current passing through that closed path. And here in the middle of the page, I wrote out the Ampere's law. Ampere's law is the integral around a closed path of the magnetic field dot the derivative of the length of that path equals the constant mu naught times the sum of the current inside that path. And the constant mu naught is written right over here, which is 4 pi times 10 to the negative 7th Tesla meter per area. And for this problem, we have a pattern of magnetic field and region of space up here. We want to find out how much current is passing through this region. So we have a magnetic field going out from the left and right sides at 0.8 times 10 to the negative 4th Tesla, and a magnetic field going out the top and bottom at an angle of 35 degrees, and a magnitude of 1.6 times 10 to the negative 4th Tesla. And in order to get the total amount of current, we have to add up all 4 of the paths, which are labeled right here, 1 through 4. But we also must choose a starting point, so we can start our path, of course. And I chose my starting point to be up here in this corner, over there. And we're going to go to the left, so we have path 1, path 2, path 3, and path 4, and so on. So my first path is going to be the integral of the magnetic field dot the derivative of the length of that path, or which can also be written as the magnetic field times the length of that path times the cosine of the angle between them. So for this path right here, my magnetic field is 1.6 times 10 to the negative 4th times the length, which is 0.6 meters right here, times the cosine between the two, which is 35 degrees, and I have that written out right here. And this is negative because the magnetic field is going in the opposite direction in which we are traveling. So we're traveling this way, magnetic field is going that way. And so for the second path, we basically do the same thing. We do the magnetic field times the length of the path times the cosine angle between them. But this time, the angle between the two is 90 degrees, and the cosine of 90 is 0, so we don't even have to count this side, it just equals 0, which is written right here. And then we're going to go on to path 3, which is the same as path 1, where magnetic field times the length times the cosine between the angle, or the angle between the two, is the exact same thing, 1.6 times 10 to the negative 4th Tesla times cosine 35 times the length. And it's negative again because magnetic field is going the opposite direction than the way we are traveling. That's our path, and that's the magnetic field. And path 4 is the same as path 2. The angle is 90 degrees, so cosine of 90 is 0, so that is just going to count as equal 0. So we just rewrote it again to equal mu naught times the current. And this, as we perform the calculations, we get negative 1.573 times 10 to the negative 4th Tesla meter equals mu naught times the total current. So if we just divide the left side by mu naught, we'll get negative 1.573 times 10 to the negative 4th Tesla meter over 4 pi times 10 to the negative 7th Tesla meter per area equals negative 125.157 amps, which is the correct unit for current, which is measured in amps, and it's negative because the current is actually going in the opposite direction than our path. So our current goes this way, but we travel this way. And this is Ampere's law.